Okay, welcome back to class, my wonderful students. This is lecture 5 out of about, I think, 28 lectures. We have exams coming up in a couple weeks, couple Tuesdays from now, I believe. And we have a bunch of clicking today, so get your clickers out. We're going to use them in just a minute. Press the clicker base is on so you can catch the frequency now, and the frequency is DD. So if you haven't used your clicker before, and this is the first time using it, hold the power button down until the rectangle in the upper left flashes, and then type in DD, and then you'll get the Go Nitro message and the Ready button. By the way, if you haven't registered your iClicker through web courses, you'll get a Go Nitro message. I just won't know it's you that's clicking. I'll pick up your clicker, but until I know that you have an NID attached to that serial number, I don't know you from Adam. So you want to make sure that you do that. And about iClickers, I put some extra or some new iClicking data into your grades page yesterday. And it's down here towards the bottom. It says L4 total 11818. And for this example, the student has a score of 2.01 out of a possible 2.02. Now, I'm going to explain what that means. All right. The score that I uploaded for for a good majority of you, it actually encodes two data. The first thing is how many questions you have answered. All right, and in this case, out of two, we only had 2 questions last Thursday. We're going to have a bunch more today, so make sure your clicker's ready to go. So the first thing that it encodes is how many you answered. It also encodes in one score how many you answered correctly. I like to keep track of both of those stats. Now, I'm going to show you how it works. For instance, and you might want to make a note of this. If you have a score of 2.01, okay, what that means is you answered 2 questions, and you got one of them correct. All right, so that's what that means. Now, we're going to do an example with this in just a second. But before we do, I want to emphasize that your participation grade, so many points out of 25 for the regular part of your semester grade, that comes out of how many you answer. All right, so the first number there encodes not whether you were correct or not, just how many you clicked successfully on. Right now, if we close the question before you send in your answer, you might not get all 2 questions answered. But if you answer them all, we'll keep track of how many you've answered. And hopefully you'll answer all 85% or more. Because if you get 85% of them answered, you get all 25 points for 10% of your semester grade. All right? Now, the other part of the score that's important is how many you get correct. There's a 4-point bonus if you get, over the course of the semester, 75 of the class participation questions correct. So don't just type in the letter C every time. Yeah, that'll get you participation, but it won't give you a shot at 4 bonus points. And believe you me, 4 bonus points at the end of the semester is going to feel mighty nice if you can snag it. And many of you will. All right? So use your brain and apply yourself as you click. I'm going to post an update to the clicker scores 4, 5, 6 times this semester, maybe. And it'll encode, as I just mentioned, how many you've answered to date and how many you got correct out of those. And it will also show you in web courses how many questions were answered as well. So it works out pretty nice. And that's going to be on your grades page, and you'll be able to look at that. And in a few weeks, I'll help you work out what your class participation grade is. If you're above 85% answer, we only had 2 questions, so you're either above 85% or you're below 85% now, so it's not hard to calculate. But if you're, in a few weeks, we'll have a whole bunch of questions on the books, and then it will be a challenge to calculate your participation grade. So we'll do some examples of that eventually. Now, as a side note, if you've looked at your grades page and you have a negative number for your score in that row of the grades page, what that means is one of 2 things. If you had a -1, that means you didn't get in a click. You got here late, or you were on the wrong frequency, or you didn't have a clicker. -2 means you're not even registered. Whatever you have, it's not registered. If you're clicking, it's not going through to your name. See, the clicking software talks to web courses, and web courses answers back with the roster. And to each person who is registered in web courses, the roster also has the serial number of your clicker. So when I get that roster from web courses, I'll know in class who's who. But if you haven't registered in web courses, I'll be able to pick up your iClicker, but I won't know who it is. Now, if that applies to you, don't worry, because as soon as you do get registered, it'll all synchronize. It doesn't forget your clicks. So if you're unregistered right now, you don't have a registered clicker, and I've got your stuff, but I don't know it's you, it's still in the records. And as soon as you do register, then it'll all go down right next to your name in the grade book. Okay, so just get them registered ASAP. And if you have trouble buying one, just kind of contact me. I know most of you have got them yet, but every once in a while there's problems. I know some students had to get, financial aid has to come through and it gets hung up and whatnot. You don't want to get too far behind. All right? Any questions about that stuff? Okay, let's keep going. A few clicker questions about clickers. Here we go. Hypothetical February 30th roundup, and your data comes in as 24.17, right? So here's the example we just had. What does it mean, 24.17? Which of these 5 options is correct? Darian is having trouble. What is it with this?
I don't know. I think there's something wrong up here because the mouse keeps going back to that.
Hold on a second. Come on, baby. Yeah, we have. What about that one? Same thing. Oh, good. We're using the touch screen now. Hey, that all works.
Yeah.
Nice. Okay. Go ahead and answer. It's working now. How you doing? Yeah, you got it? Okay. You got a check mark? Perfect. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Question. What's your question?
Oh, no, it was closed for a sec,
Okay. Go ahead and close it. Yeah, question.
My thing said closed the whole time. I couldn't send in an answer.
It was open up here.
It was open up, if that happens again, hit the refresh key. Hit the refresh key now, in fact. All right. So yeah, option E is correct. And here's how if you didn't, a few of you didn't answer correctly. Yeah, here's 24.17. So the whole number part is how many you've answered, all right? And then the second, the hundredths decimal part of the number is how many you got correct. All right, now, same data, another question, all right? 24.17, and there were 28 questions asked, right? What is your participation percentage? Are you clicking?
Yes.
You got it? Okay. Anybody not getting a frequency on? Kenneth, what is the frequency? All right, these guys are doing good. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ching. There's 142 students who just answered. Go ahead and show that, dear. And so you can see here, and most of you guys got it right. But you know what that means? That means almost all of this class is registered and clicking. So that's good. Lovely. Okay, back to regular, please. Yeah, correct here. So, and if you got that one wrong, here's how you do it. You take the 24 divided into 28, or 28 divided into 24 is 0.857, and that's your participation percentage. And you can make a note. You should be, with the clicker questions, most of the time you want to make a note of them, include them in your notes. This particular student would get all 25 points, even though they have not been here they have not answered. They might have, 28 questions, they didn't answer 4 of them. They might have missed a lecture. Last 3 rows empty, please. Can you move forward, you guys in the back there? Last 3 rows, I want them to be vacant. Okay. Yeah, those guys over there, they're not getting the message. Okay. Yeah, move forward, please. Yeah, so this particular person, 4 questions, they might not have been there. By the end of the semester, it's probably going to be like 2, maybe 3, depending on the lecture, lectures that you can burn and still get 85% of the questions answered. So that works out nice. Okay, another question, multiple choice. Your roundup comes in as 24.17. Do you have 75% or more correct? This one's yes or no. And, right. This is nice, using this touch screen. Matter of fact, let's do that now. even though it makes you lean over. You know, I could probably even operate it. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 143. Nice. Amazingly, some of you did not get this right. The answer is no. You don't have the 75% level. Here's how you figure it out. You go to your score, 24.17, and then you take the decimal part out and just treat it like a whole number. All right. It tells you how many you got correct out of 28. All right. And that happens to be 60.07 or 60.7%. So you're below 75% for now. Now this is the mythical February 30th update. But you know the thing about it is there's no February 30th this year.
This year.
Or in any other year. So this is a totally mythological update. But it is pretty much halfway through the semester, so you still have a chance to get it up to 75% and definitely bear down and start crushing things. All right? So let's keep going and talking about velocity. Last time we were talking about velocity graphs, and we had on our abstract graph our unphotographable display of information. The horizontal axis was the time axis, and the vertical axis is, for instance, the x component of the speed. So how fast you go to the right or how fast you're going to the left. All right. A negative number means that you're going to the left, and a positive number means. So this one is, the graph is up in the top half. That doesn't mean you're moving upwards. It means you're moving rightwards. So and that's why I say it's abstract. You really got to think, and you can make a picture or a map of a spatial map from this, but this itself is not a two-dimensional map. So do not be deceived. Try to think of it as an abstract. So this is like, you know what it's like? It's like reading a word. A word is in a book is made up of symbols, and the symbols all have meaning. Like the letter A has a meaning in itself, but when it's in a word, ice cream, that's two words, it has a completely different meaning. So you got to read it and think, all right, what is it? What is it? You have to decode it. Those letters stand for the word ice cream, or whatever it is whatever word it is that you're looking at. Okay, and the same thing here. Now the height, the rise, like this line has a rise and a run. It's got a slope. The slope has meaning. And the rise is, the change in the velocity, delta V. All right? And so this one, you might even ask yourself, how is the velocity changing here? I mean, like right here, up here at the beginning of the graph, I'm up at positive 2 meters per second. So this would mean that I'm actually moving in that direction at time t equals 0. But 2 seconds later, I'm over here at the end of the graph down here and below the time axis. So that means I'm in negative v subscript x, and that means I'm actually, after 2 seconds, I'm actually moving to the left. All right? And so we're going to analyze this. All right? One of the other things that we did last time was we made the distance triangle and we made a distance rectangle. We talked about that. The interpretation of the area of those, had a physical meaning, the distance traveled. And we're going to do a lot of work with that today, including some work on the document camera to do some deluxe distance polygon activity. All right, so what I want you to do for the next few clicker questions is make a good sketch of this graph. All right. Raise your hand if you have Netflix, or you can use somebody's Netflix. Okay, good, because your homework is going to involve Netflix tonight. If you don't have Netflix, I don't know. You'll have to figure out some way to borrow somebody's Netflix or whatnot. All right, next question. Here we go. So this is the graph, and here's a question about the graph. All right, now the graph is still in there. Now, how would you interpret, read carefully, which option is a good description of what the object is doing? Look at the graph, read the sentences. Look at that. That's interesting. I want you to, and hey, you guys, when you're in class like this, you can talk with your neighbor and talk it over. You know, if you have somebody that's sitting next to you and they're not unfriendly. Okay, if nobody's sitting next to you, God bless you, but if you're with a friend, you can tap them on the elbow and ask him. Or they can ask you. And students, it's a great way to learn because, you know, two heads are better than one, they say. Iron sharpens iron. And your classmates can help you learn. Yeah, so you can eliminate that. And eliminate Waldo. Yeah, you better eliminate that. $30. This is very interesting. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Go ahead and show them this display, please. All right, here's the correct answer is C, and a good pile of you answered C, but not a majority. And a good pile of you answered D, but that's wrong, but it's not a majority either. So this one, we better take a look at this. So go back to your sketch, and let's take a look at it. This is the correct answer. Can you switch over to the display, please?
Oh, I thought it did.
Yeah, sorry. We need better chairs in here. These. All right, so this is the correct answer, C. And let's just take a look at it. All right. Now this is what I say. You have to think in an abstract manner and read the graph and try to figure out what it means. Now up here, the graph is above the time axis. So that means you have a positive velocity. It's not 2 meters per second the whole way, but it's still positive. And because it's positive, that means you're starting out to the right. But you're slowing down because eventually, in the middle, you get you come to a stop. But down here, all right, in this half of the graph, you're negatory. Right? So that means you're cutting to the left over here. Right? Now, if you think about it, if you're walking to the right and later you're walking to the left, that means you have to turn, you have to stop, turn around, and change your direction. And that happens right here. All right? So this crossing point where the graph crosses the time axis, that's where v equals 0. Vx equals 0 on the time axis. And so that's the stopping point. Right? So label that in your notes. That's the stopping point. You know, however far out that is. Oh, and you know, we can do a distance calculation from this, because we can figure out a distance triangle. And we're going to put that together here in a second. All right, so this one initially moves horizontally to the right. The graph is above the time axis. Right here it's at 0. It crosses the time axis. Vx is equal to 0. It stops. And just for a second, and then it starts moving back to the left in the second half of the motion. All right? And let's take another question here. Question, I don't even know what this is. Question 5. The run of this graph is 2 seconds. The meaning of this is you know, so in terms of rise over run, you know, do you remember that from like high school algebra class? That's where I learned it. Rise over run. The slope. Rise over run, the tangent. The tangent of the slope angle. Did you know that the tangent becomes enormously important in the theory of relativity? It's because it's the tangent, the rise over the run is the speed. It encodes the speed of an object. Distance and time, just like this. Except in relativity, it's a little different looking than this. But yeah, it encodes the speed, and the speed is everything in relativity. The speed of the observer. So. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Bing. Yeah, you guys got it. This is the run, and that's the duration of the motion, you call it. You know, or that's the time. Now, make a note of it. You could say this is the time interval, or the elapsed time for the motion. You know, there's a bunch of different ways to say it. All right. Now, next question. Question number 7. Is that 6 in Espanol?
No, that's 7.
It is? Okay. 7 minus 1. Question 6.
You could also just say 6.
The 6. Yeah, in other words, 6. I'm Hispanic, but I don't know Spanish. I don't even know. I know German. I don't know Spanish. The rise of this graph, minus 4 meters. What? How can you have a negative number for the rise? Isn't that kind of like a contradiction? No, you're dipping. It's dipping. You're dipping as you go to the right. So what's the interpretation of that one? Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, good. Go ahead and show this. We have a little bit of controversy here. The majority of you voted for D, and D is correct. the object's delta V. A significant group voted for A and B. Go back to the laptop, please. So A and B, the distance traveled. What is the distance traveled? It's in meters. Yeah, the distance is meters. But what in this graph corresponds to the distance traveled? Not the run, not the rise, not the slope, the area of the polygons. The object's acceleration. No, it's not the, you know what the acceleration is? Let's do this question. The rise over the run. The graph is, so this is like you take the rise, divide it by the run. The run is 2 seconds, the rise is -4. So -4 meters per second divided by 2 seconds is -2 meters per second. So what is that actually equal to? If you did the reading, you know. My stomach is rumbling badly. Yeah, that's right. 20 seconds to vote. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, now the answer to this one, most of you got it correct, is B. And -2 meters per second, with that, go ahead and write that number down. -2 meters per second. What that means is if you're moving to the right, you lose 2 meters per second of speed for every second of travel. Let me repeat that. If you're moving to the right, in other words, you have some positive speed, you lose 2 meters per second for every second of travel. And that's what happens here. The first second, he's lost all of it. He's down to 0. Also, it means -2 meters per second. It also means if you're moving to the left, you're gaining 2 meters per second of leftward speed, i.e. -2 meters per second, for every second that you're accelerating to the left, right? And that's why from t equals 1 second to t equals 2 seconds, he's acquired 2 meters per second, but it's negatory. He's below the time axis, right? So it slows down, and then it starts acquiring leftward speed or leftward velocity. Question?
For the meters per second, can we put meters per second squared or is it?
Yes, you may. Definitely. And I've got a slide for that in just a second. Question?
So is this basically like saying that a person is moving forward, stopping, and then moving backwards to the same spot you're at?
Yeah, it is. And so here's one way you could think of it. If, okay, like in space, you know, like the Klingons, they put a tractor beam on somebody, you know, like another spacecraft. All right, so the tractor beam is acting to the left, say, right? You're moving to the right, so the first thing the tractor beam is going to do is slow you down. Then it's going to stop you, and then it's going to move you back towards the Klingon bird of prey space vessel. Okay, so just think, so if you can think of Star Trek, you can figure it out. Yeah.
So would it be stopping and moving back to the same spot, or would it be stopping and then moving further backwards?
Is it, oh, the question is it stopping and moving back to the same spot? Ding, 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 ding. Exactly. It's exactly what happens. and we're going to get to that in a second. You're way ahead of the game here. Anyways, let's look at this formula. Here it is. Acceleration, rise over run on this graph. Formula-wise, delta V over delta T. We've talked about that already. Yeah, so that's, so it works out to minus 4 meters per second divided by 2 seconds of run. All right, to the right. And so that's minus 2 meters per second. And as one of the students in the back was asking me, Dr. B, instead of writing minus 2 meters per second, could you write that as minus 2 meters per second squared? And the answer to that is yes, you may. And it is a little more compact, so it's nice if you, but either way is fine. You know, if you're writing a message to me, you know what, the messaging system inside web courses, if you're writing a message to me about acceleration, you'd have to write it meters per second. But if you're in discussions, they have a little formula editor in there. You can write it as meters per second squared, so it works out pretty nice. Okay, I have to pause the recording here for just a second. I see. All right, that's better. All right, now, next question. And this has to do with, what is your name up here in the front? What is your name again? Kadia, good. Kadia was up here asking me a question about, where does it end up? And this next question asks that very thing. What is the area of the first distance triangle here? And go ahead and sketch it in and shade it here. I'll shade it in. Go ahead and shade that in on your notes. And compute the area of it. Do you know how to do that? 1/2 base times height. Easy as taking a walk through the park. So what's the area of that first distance? We got 2 distance triangles here, by the way. One above the time axis, one below it. All right. 30 seconds to type in your answer. Boy, we got a bunch of questions. You guys are smart. Very good. Or as Mr. Burns would say in The Simpsons, excellent.
Is that where you got that from?
Yeah, although I've never actually watched an episode of The Simpsons. I watched The Simpsons movie, but I didn't watch it on TV.
So you missed out on like all the actual good Simpsons stuff.
Yeah, but I do know that this legend of Mr. Burns, he's some kind of a guy, and he says excellent a lot when he's being devious. And Bart's being mischievous, and Mr. Burns is being devious. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, you guys did good. Base times height, and in this case, it's 0.5 times 1.0 times 2.0 meters per second. Okay. For this particular triangle, right, so that works out to 1 meter. And that is the distance it travels. Go ahead and make a note. That is the distance you travel to the right. But now, so C is the correct option on this one. But now, you're in the second half of the motion, from t equals 1 second to t equals 2 seconds, you got some splaining to do because you're going to the left now. Right? And by the way, this formula, or this calculation, corresponds exactly to 1/2 at squared, the distance triangle formula. All right, so let's make a spatial map now. And here we go, Katia. We're getting to your question, your statement. Go ahead and make a picture of the x-axis. All right, so this is going to be a set of locations. And if you were to take a photograph or a series of photographs of this object in motion, it would look a little bit like this sketch. All right? So this is not abstract, it's more physical. All right? It's geometric. All right? So from t equals 0 to t equals 1 second, ding, it goes 1 meter. Now you don't have any more strobe photos except for these two, t equals 0 and t equals 1. But, that's where it is. Go ahead and make a note to yourself at t equals 1.0 at that dot out there. Make a note. V equals what? What's the speed equal to out there at 1 meter? It's 2 meters per second, right? Or is it? What is the think? What is the speed there? No. It's 0. It stopped. All right? Now, Katie, here we come. Let's try another clicker question. All right? Let's bring this all the way home. All right? And I'll keep the same picture. Now I have all these pictures up here. Here's the question. What is the position at time t equals 2.0 seconds? And this is now calculating with the second distance triangle. Okay, so it's up there. I just burned it in. All right. Now it's going leftward. I'm not answering your question. I want you to think. From t equals 1 to t equals 2, it's going leftward. So at the end of the second, at t equals 2.0 seconds, where in the world is the object? It's going over here, it's going over there, it's going like this. Okay? I see people pointing over here, I see people pointing over here, I see people going like this. It's not going in a circle, but it's going over here. Good. I grew up in an Italian, just at the edge of an Italian neighborhood in New Jersey. And they're famous for talking with their hands, all those guys. In our neighborhood, they were anyways. So I always love seeing you guys talking with your hands and just gesticulating and stuff like that. 20 seconds to make your decision, the decision of destiny. Wow, 9 questions today. Ooh, baby. So that means an average of 5.5 for the first 2 official lectures. Actually, I think we have some more after this. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And go ahead and show the display of this, please. I have to say you guys are doing great. That is the correct answer. Go back to the laptop, please. D is the correct answer. And so it's moving left. it moves, it's the same size triangle, but now it's moving left, so you have to construct it as moving left 1 meter, right? And so that means that the area under the time axis, if your distance polygon is underneath the time axis, you count it as a negative distance or a backup. All right? So you've ended up over here, back where you started. All right? And so now, and here's the, Katie, here's where, look at the animation now. All right, here it comes. Right? It goes out to 1.0 and then straight back. Under this velocity, for this velocity graph, if we have a different motion, it might be different. All right? Question?
Do we have to use the graph like that one, or we just use the other one?
You have to use it if I'm asking about it. But the thing is, there's a lot of different ways to describe the motion of something. So I might describe it in terms of, positions down here. But if I do describe the motion in terms of a velocity graph, you know how to make and extract a map of positions. Okay? Those are equivalent. Okay? And so you can move back and forth between the two. All right? So the velocity graph is actually pretty important. Because velocity is something that we can see. We can see something that's moving. Okay? And you can see a position of something. You can time something. You can't see time, but you can measure time, with a pendulum or any other timekeeping device. And you can balance things in a balance for mass, so many kilograms of mass. But that's about it. All right, so this stuff becomes pretty important, at least to know the basics of the velocity graph. So let's go and make a summary to our dean, Professor Galileo, about what we know. Constant velocity, delta x equals v delta t, speed times time. D equals vt, basic. The velocity graph is a horizontal line segment. And now we can handle one that's below the time axis. All right, we just did a triangle below the time axis. We could do a horizontal line below the time axis. Just means something's going to the left. The polygon associated with that velocity graph is a distance rectangle. All right. Now, if something's accelerating from rest, so from vi equals 0, or if it's accelerating to a stop, it's slowing down to a stop, vf equals 0, we have a fairly simple formula. Delta x equals 1/2 at squared. That's this one. D equals 1/2 at squared. Now, when we start talking about exact positioning in 2 dimensions, we're going to have to use a little bit fancier of an equation. And I'll show you how to do that probably Thursday. All right. So for this one, the velocity graph is a sloped line segment. Some degree of steepness, some tilt angle. So there's a rise over the run. The one we just studied, -2. But you could have, a positive 7.2 meters per second for the rise over the run, i.e. the acceleration. But you still have a distance triangle of some kind to figure out, figure out the rise, figure out the run, 1/2 at squared, bing, you got your distance. But now, here's what I want to ask you. what if the velocity does not change uniformly? In other words, what we were working with was a triangle with a straight hypotenuse, always dipping at the same dip rate, same slope. But what if you have something that doesn't change uniformly? Well, we're going to talk about that now. And this brings us into this famous movie, Hidden Figures, which I really love, which I recommend to you for your homework. Although it is not in Netflix, unfortunately. Well, you can't stream it Netflix. You can order the DVD. But if you know anybody that's got a DVD of Hidden Figures or a Blu-ray of Hidden Figures, definitely watch it. Because this movie, unlike a lot of stuff from Hollywood, is a real thing. There really is, a Dorothy Vaughan. Here she is right here. She's the one in the movie that taught herself Fortran to control spaceflight. Can you imagine? And all she knew was, she was a very skilled mathematician, but nobody back in those days knew what they were doing. You know what Einstein said once? He said, if we knew what we were doing, it would not be called research. So Dorothy Vaughan, the real Dorothy Vaughan, she really did teach herself Fortran so that she could control all the mathematics in those big fancy new IBM computers they had, and make those calculations. And by the way, if you have an iPhone or an Android phone, your computer is about 9,000 zillion times more powerful than the ones that these guys were working with. And the ones that these guys were working with back in the late 50s and early 60s, those computers filled a room this size. Several of them would fill a room this size. But you got it in a phone that you could put in your pocket. It's amazing to think about. So Hidden Figures. So what we're going to study here is this question: how do you handle the trajectory of a spacecraft? How do you, if you have something that is launching from Mission Control or from Kennedy Space Flight Center, which in the movie they were working with Mercury space, John Glenn and Alan Shepard and those guys, and they wanted to bring them back safely to the Earth. John Glenn went into orbit, a few orbits, then brought him safely, and it was considered dangerous. So getting the calculations right for them was not an easy thing. So here's an example. Go ahead and make a sketch of this. Here's a velocity graph, v subscript y, the vertical component of the velocity, vy. All right, and it's changing, but it's not a straight. It's not like a hypotenuse of a right triangle. Right, so it's speeding up, and then it's kind of leveling off a little bit, and it's speeding up again. And hey, you guys, when you're looking at the flight of a rocket boosting off from Kennedy Space Center, here's what's changing, what makes it difficult. The rocket fuel is a huge fraction of the total weight of the rocket. It's the payload, the astronaut up there on the very top of the rocket, or the satellite that they're trying to launch, very small fraction of the total weight of the rocket. Most of it is the rocket itself and the fuel that it has to carry to get one little teeny guy in this little can, this little metal can that's sealed against the atmosphere up into space. Is very small. And what happens is you ignite the rocket fuel, right? You got a rocket motor. You know, when they take off, they say, 3, 2, 1, ignition, liftoff. So they ignite the rocket fuel in the rocket motor, and the way it works is, according to Sir Isaac Newton's laws of motion, the rocket fuel goes out the back end, and the rocket goes to the front, goes up. So the rocket, all that ignited rocket fuel goes at extremely high velocity out the back end, and the rest of the rocket goes the opposite direction. Equal but opposite reaction. Newton's third law, that's it. All right. Now the problem with that is, as you lose all that rocket fuel, the rocket becomes lighter, and therefore it becomes easier to accelerate. And therefore, the speed is going to be changing in a non-uniform way. It's not going to be nice, constant 2 meters per second vertically. I mean, they'd like that, but that's not what they get. So they have to be able to deal with this, and we're going to deal with it too. And the way that we're going to deal with it today is by using the document camera. So let me pause the record. Talk to Darian about highlights. She's the mistress of...
About highlights for the picture?
yeah.
Oh, okay. What's going on with them?
I have the book.
I clicker issues,
The steps are what first.
but I
You have eye clicker issues?
ordered it and